This is my video lab report for Lab 3. In this lab, I examined the orbit of a star around a black hole. Setting the system as the star, I used the position versus time data points from the star's orbit, which was given through a CSV file, and the momentum principle and the equations derived from the momentum principle in order to calculate the mass of the black hole. Now, let's take a look at some of the equations that I used in this experiment. From the momentum principle, I have the equation Fnet equals dp dt, which in turn equals Fnet parallel and perpendicular, as well as dp dt parallel and perpendicular. dp dt parallel and dp dt perpendicular and the Fnet parallel and perpendicular are parallel and perpendicular components of the net force and the change in momentum over time. These components help us examine and understand curved motion. dp dt perpendicular, for example, can be calculated from the mass, the velocity, and the radius of the kissing circle, which is the circle that the curved motion is tangent to. In this particular case, the center of the kissing circle is the black hole because it is the only agent acting on the star. Lastly, Fgrav will act as the net force, once again because the black hole is the only force acting on the system and it is a gravitational force, so this equation is particularly important here because it allowed me to solve for the black hole's mass. In order to better understand this, let's take a look at a graphic that shows the orbit of a planet around the sun. Here we see the planet's velocity. This is the net force because the sun is the only agent acting on it, similar to our black hole and our star. Here's the perpendicular component of the net force or gravitational force, and here is the parallel direction. Having the positions of the star and the black hole that was provided, I was able to calculate the distance between the star and the black hole using the equation that the distance equals the square root of the x component of the distance squared plus the y component of the distance squared. To perform these calculations, I used a VPython code that was provided to do all of the heavy lifting. After plugging in the star's mass, the delta t, and attaching the CSV file star data rushing3godtech, which allows us to find the delta v and the delta t from the change in positions over time provided in the CSV file. I then set up my equations based on the momentum principle. Here we can see some equations that were shown earlier in the video. These equations here, but just translated into Python code. As we can see right here, for example, Fnet equals delta P over delta T is exactly the same as our example equation shown earlier in the video. At the end of the code, I had my program print the time elapsed, the magnitude of the net force, in the parallel and perpendicular direction. Using the positions from the CSV file and the position of the black hole, I use the equation previously stated to find the distance, our x component squared plus our y component squared, and then the square root of that. Taking the gravitational force equal to the net force, I solved for the mass of the black hole, as we can see here, just in terms of Python, and then printed the mass of the black hole here. After running the module, we can see the net force represented by the yellow arrow, the perpendicular of the net force represented by the blue arrow, and the parallel force represented by the small black arrow here. The net force will always point to the black hole because our black hole is the only agent acting on our system. In this case, the fact that we have a small parallel net force component suggests that our star's orbit is not a perfect circle, but rather an ellipse, because there would be no Fnet parallel if this was a constant rate, and a constant rate tells us that it's a circular motion. And with the program following its instructions, we can see the mass of the black hole here in kilograms. Speaking of all this talk about Fnet and dp/dt, what exactly does that mean? If you recall from earlier in the video, Fnet and dp/dt both have a perpendicular and parallel component, as can be seen here for this net force, with our perpendicular and parallel components. Even though mathematically Fnet equals dp/dt, the reality is that Fnet is the force acting on the system, and the change in momentum over change in time, dp/dt, is the reaction. Simply put, Fnet is the cause, and dp/dt is the effect from that cause. Having successfully completed this experiment, we know that we can take the position and time data of a star's orbit around a black hole to find that black hole's mass, as long as we have the star's mass, of course. But what if that black hole was suddenly replaced by another black hole of a different mass? Could we calculate its new mass? The answer is yes. Since the mass of the star doesn't change, we already have that. Then we would have to wait for the star to change its orbit so that we could redo the entire experiment based on the new data points acquired from the star's new orbit. With that said, that's all I have for my video lab report, and thanks for watching.